Okay, hi everyone. Welcome back to this video series on data center Ethernet cabling. Ethernet cabling. A discussion about Ethernet cabling is an important one, especially if you are planning on taking the Cisco exams. You need to really understand the following three types of cables: straight through cable, crossover cable, rolled cable. Straight through cable. The straight through cable is used to connect the following devices: host to switch or hub, router to switch or hub. 4 wires are used in straight through cable to connect Ethernet devices. It is relatively simple to create this type. Figure 3.6 shows the 4 wires used in a straight through Ethernet cable. Notice that only pins 1, 2, 3 and 6 are used just to connect 1 to 1, 2 to 2, 3 to 3 and 6 to 6, and you'll be up and networking in no time. However, remember that this would be an Ethernet only cable and wouldn't work with voice or other LAN or WAN technology. Crossover cable. The crossover cable is used to connect the following devices: switch to switch, hub to hub, host to host, hub to switch, router direct to host. Same 4 wires used in the straight through cable are used in this cable. We just connect different pins together. Figure 3.7 shows how 4 wires are used in a crossover Ethernet cable. Notice that instead of connecting 1 to 1, 2 to 2 and so on, here we connect pins 1 to 3, 2 to 6 on each side of the cable. Rolled cable. Although rolled cable isn't used to connect any Ethernet connections together, you can use a rolled Ethernet cable to connect a host EIA TIA 232 interface to our router console serial communication COM port. If you have a Cisco router or switch, you would use this cable to connect your PC running hyperterminal to the Cisco hardware. 8 wires are used in this cable to connect serial devices, although not all 8 are used to send information, just as in Ethernet networking. Figure 8 shows the 8 wires used in a rolled cable. These are probably the easiest cables to make because you just cut the end of one side of a straight through cable, turn it over and put it back with a new connector. Of course, you can have the correct cable connected from your PC to a Cisco router or switch console port. You can start a hyperterminal to create a console connection and configure the device. Typically, we'd use a new terminal emulator such as Secure CRT or PuTTY. See the configuration as follows: open hyperterminal and enter a name for the connection. It is irrelevant what your name is, but I always just use Cisco. Then click OK. Choose the communication COM port, either COM 1 or 2, whichever is open on your PC. Now set the settings. The port values 2400 bps and no flow control hardware will not work. You must set the port settings as shown in figure 3.9. Notice that the bit rate is now set to 9600 and the flow control is set to none. At this point you can click OK and press the enter key and you should connect to your Cisco device console port. We've taken a look at the various RJ45 unshielded twisted pair UTP cables. Keeping this in mind, what cable is used between the switches in figure 3.10? In order for a host to ping host B, you need a crossover cable to connect to the two switches together. But what type of cables are used in the network shown in figure 3.11? In figure 3.11 there are a variety of cables in use. For the connection between the switches, we'd obviously use a crossover cable like the one we saw in figure 3.7. The trouble is we have a console connection that uses a rolled cable, plus the connection from the router to the switch is a straight through cable, as is true for the hosts to the switches. Keep in mind that if we had a serial connection, which we don't, it would be via 35 that we'd use to connect to a WAN. Figure 310 RJ45 UTP question. Figure 311 RJ45 uses UTP cable question 2. Data encapsulation. When a host transmits data across a network to another device, the data goes through encapsulation. It is wrapped with protocol information at each layer of the OSI model. Each layer communicates only with its peer layer on the receiving end to communicate and exchange information. Each layer uses protocol data units, PDUs. These hold the control information attached to the data at each layer of the model. They are usually attached to the header in front of the data field, but can also be the trailer or end of it. Each PDU attaches to the data by encapsulating it at each data layer of the OSI model, and each has a specific name depending on the information provided in each header. This PDU information is read only by the peer layer on the receiving device. After it's read, it's stripped off and data is then handed to the next layer up. Figure 312 shows the PDUs and how they attach control information to each layer. This figure demonstrates how the upper layer user data is converted for transmission on the network. The data stream is then handed down to the transport layer, which sets up a virtual circuit to the receiving device by sending over the sync packet. Next, the data stream is broken up into smaller pieces and the transport layer header is created and attached to the header of the data field. Now the piece of data is called a segment, a PDU. Each segment can be sequenced so the data stream can be put back together on the receiving side exactly as it was transmitted. So I see here data encapsulation, upper layer TCP header, upper layer IP header data, LLC header data, MAC header, data FCS, application presentation session transport, network, data link and physical. So this here would be the OSI model. Each segment is then handed to the network layer for network addressing and routing it through the internetwork. Logical addressing, for example, IP, is used to get each segment to the correct network. The network layer protocol adds a control header to the segment handed down from the transport layer, and what we have now is called a packet or datagram. Remember that the transport and network layers work together to rebuild a data stream on the receiving host, but it's not part of their work to place their PDUs on the local network segment, which is the only way to get information to the router or host. It's the data link layer that's responsible for taking packets from the network layer and placing them on the network medium, cable or wireless. The data link layer encapsulates each packet in a frame, and the frame's header carries the hardware address of the source and destination nodes. If the destination device is on a remote network, then the frame is sent to a router to be routed through an internetwork. Once it gets to the destination network, a new frame is used to get the packet to the destination host. To put this frame on the network, it must first be put into a digital signal. Since the frame is really a logical group of ones and zeros, the physical layer is responsible for encoding these digits into a digital signal, which is read by devices on the same local network. The receiving devices will synchronize on the digital signal and exact decode ones and zeros from the digital network. At this point, the device's reconstructed frames run a CRC and then check the answer against the answer in the frame's FCS field. If it matches, the packet is pulled from the frame and what's left of the frame is discarded. The process is called de-encapsulation. The packet is handed to the network layer where the address is checked. If the address is matched, the segment is pulled from the packet and what's left of the packet is discarded. The segment is processed at the transport layer, which rebuilds the data stream, acknowledges to the transmitting station that it received each piece. It then happily hands data stream to the upper layer application. At a transmitting device, the data encapsulation method works like this. User information is converted to data for transmission on the network. Data is converted to segments and a readable connection is set up between the transmitting and receiving host. Segments are converted to packets or datagrams and a logical address is placed in the header so each packet can be routed through the internetwork. Packets or datagrams are converted to frames for transmission on the local network. Hardware Ethernet addresses are used to uniquely identify hosts on a local network segment. Frames are converted to bits and a digital encoding and clocking scheme is used. To explain this in more detail using the layer addressing, I'll use figure 3.13. Remember that a data stream is handed down from the upper layer of the transport layer. As technicians, we really don't care who the data stream comes from because there's really a programmer's problem. Our job is to rebuild the data stream reliably and hand it to the upper layers on the receiving device. Before we go further in our discussion of figure 3.13, let's discuss port numbers and make sure we understand them. The transport layer uses port numbers to define the virtual circuit and the upper layer process, as you can see from figure 3.14. The transport layer, when using a connection orientated protocol, that is TCP, takes the data stream, makes segments out of it and establishes a reliable session by creating a virtual circuit. It then sequences numbers. Each segment uses acknowledgements and flow control. If you're using TCP, the virtual circuit is defined by the source and destination port number as well as source and destination IP address. That's called a socket. Remember, the host just makes this up starting at port number 1024. 0 through 1023 are reversed for well-known port numbers. The destination port number defines the upper layer process application. The data stream is handed to when the data stream is reliably rebuilt on the receiving host. Now that you understand port numbers and how they are used at the transport layer, let's go back to figure 3.13. Once the transport layer header information is added to the piece of data, it becomes a segment, is handed down to the network layer along with the destination IP address. The destination IP address was handed down from the upper layers to the transport layer with the data stream, and it was discovered through name resolution method as the upper layers probably DNS. The network layer adds a header and adds a logical addressing IP address to the front of each segment. Once the header is added to the segment, the PDU is called a packet. The packet has a protocol field that describes where the segment came from, either UDP or TCP, so we can hand this segment to the correct protocol at the transport layer when it reaches the receiving host. The network layer is responsible for finding the destination hardware address that dictates where the packet should be sent on the local network. It does this by using the address resolution protocol, AIP. IP at the network layer looks at the destination IP address and compares that address to its own source IP address and subnet mask. If it turns out to be a local network request, the hardware address of the local host is requested via an ARP request. If the packet is destined for a remote host, IP will look for the IP address of the default gateway router instead. The packet, along with the destination hardware address of either the local host or default gateway, is then handed down to the data link layer. The data link layer will add a header to the front of the packet, and the piece of the data then becomes a frame. We call it a frame because both a header and trailer are added to the packet, which makes it resemble bookends on a frame, if you will. This is shown in figure 3.13. The frame uses an ether type field to describe which protocol the packet came from at the network layer. Now, a cyclical redundancy check, CRC, is run on the frame, and the answer to the CRC is placed in the frame check sequence field found in the trailer of the frame. The frame is now ready to be handed down one bit at a time to the physical layer, which will use bit timing rules to encode the data in a digital signal. Every device on the network segment will synchronize with the clock and extract the ones and zeros from the digital signal and build a frame. After the frame is rebuilt, a CRC is run to make sure the frame is okay. If everything turns out to be all good, the hosts will check the destination MAC and IP address to see if the frame is for them. Chapter summary. In this chapter you learn the fundamentals of Ethernet networking, how hosts communicate on a network, and how CSMA-CD works in an Ethernet half duplex network. I also talked about the differences between half and full duplex modes and discussed the collision detection mechanism. CSMA-CD also in this chapter was a description of the common Ethernet cable types used in today's networks. And by the way, you'd be wise to study the section really well, for Ethernet frame types were discussed and part of the CCNA data center objectives. Important enough to not gloss over. This chapter provided an introduction to encapsulation. Encapsulation is the process of encoding data as it goes down the OSI stack. So I'm going to leave it here this evening for this video. If you like listening, please consider like, sharing and subscribing. Thank you.